One tenant's batch should not freeze every customer's LLM jobs. Hatchet groups runs by tenant and round robins worker capacity before the queue gets monopolized. You'll walk away with a setup that fairly queues language model jobs by tenant, caps active work, and rotates turns. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Multi-tenant model serving looks harmless until one noisy customer floods the system. Suddenly, everyone sees latency spikes and costs explode. What you want instead is predictable latency and bounded spend. Not a single tenant hogging all the workers. Hatchet makes those fairness rules explicit, so the orchestrator enforces limits instead of a dozen brittle rate limits scattered around. At a high level, fairness here means two things. Group work by tenant so each customer gets a share. Then, schedule active work round robin so no single group holds every worker. Picture 3 tenants and 2 workers. With the right rules, only 2 runs per tenant are active, and Hatchet rotates which tenant grabs the next free worker. We'll build a small demo. Create a Hatchet client, declare a tenant-aware concurrency rule, register an LLM task, submit a non-blocking batch, and finally add a tier-level guardrail. That sequence shows where fairness lives and how you can extend it for monitoring and cost control. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's create the Hatchet client that everything else will use. This snippet creates the smallest Hatchet connection point for the queue demo. A shared LLM queue only helps if every worker and caller talks to the same orchestrator. So, Hatchet debug true becomes the object we build on in later snippets. There is no task yet, just the official Hatchet SDK client that will own workflow definitions, concurrency policy, and run submission. The client name check gives a tiny visible confirmation before we add scheduling rules. The output shows the active Hatchet client class, which matters because every fairness rule will hang off this object. With the client available, we need to declare the fairness boundary that will actually cap concurrent work per tenant. This example defines the fairness boundary before any expensive LLM work runs. LlmJob makes tenant, tier, and prompt explicit inputs. Then, ConcurrencyExpression tells Hatchet to use input.tenant as the dynamic concurrency key. Max runs equals 2 means each tenant can have only 2 active runs for this workflow, while ConcurrencyLimitStrategy.groupRoundRobin keeps queued groups rotating instead of letting one large batch dominate. Raising max runs improves a tenant's burst throughput, but increases shared downstream pressure. Lowering it protects latency for other tenants more aggressively. The output shows the exact grouping expression that makes the cap per tenant. Next, we attach the real LLM work, so runs must pass the rule before executing. This code puts the LLM-shaped work behind the Hatchet workflow policy. The @LLMWorkflow.task decorator registers call LLM, so runs submitted to LLM workflow must pass through the tenant concurrency rule before this function executes. The toy tokens calculation stands in for the cost signal you would usually get from a model provider or tokenizer. Sample keeps the on-screen input readable while still showing how the same LlmJob schema flows into the task. The output shows a computed token estimate, which matters because fairness protects both latency and spend. Now we try a burst of submits to see how the queue accepts work without blocking the caller. This snippet turns the policy into a queuing action with a mixed tenant burst. LlmWorkflow.runNoWait job submits each LlmJob to Hatchet and returns immediately, which is the shape you want from an API handler that should not block on an LLM call. The important contrast is that Acme can submit multiple jobs, but Hatchet still evaluates the workflow concurrency key before dispatching active work. Tenant count is computed from the same jobs list, so the printed result ties the burst back to the fairness groups. The output shows how many tenants and jobs entered the queue, which is the first incident debugging number to check. Finally, we add a secondary rule to protect tiers as well as tenants. This example adds a second guardrail without replacing the tenant cap. A production LLM queue often needs one rule for noisy customers and another for a broader pool, such as input.tier, because free tier traffic and pro tier traffic may have different capacity budgets. Hatchet accepts a list of ConcurrencyExpression objects in Hatchet workflow, and a run must satisfy the configured concurrency rules before it can execute. Group round robin remains the scheduling strategy, so active groups continue to rotate fairly inside each limit. The output shows the number of fairness rules now attached, which matters because the baseline protects both tenants and shared service tiers. In a real deployment, you would wire the token estimate to your provider's cost model and ship observed token usage into Hatchet as a signal. You would also surface the queue depth and per-tenant active counts to your monitoring dashboards, so ops can see when a tenant is consistently hitting its cap. This pattern gives you 3 clear outcomes. It enforces per-tenant concurrency, so one customer cannot starve others. It keeps capacity usage predictable, and it gives you a place to add cost-aware signals. Use it when multiple customers share an LLM fleet and you need bounded spend or steady latency. One caveat: if you set caps too low, you can increase tail latency for heavy users, so balance those numbers against your business priorities. A practical next step is to tune the max runs values by tier. Run this demo against a week of representative traffic and adjust max runs for the free tier and pro tier independently until latency and cost targets align. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.